Morning, everybody. We're going to look at the nucleus and specifically Rutherford, Geiger, and Marsden's experiment that we just kind of briefly talked about when we introduced atomic models. We're going to look at the results of Rutherford's scattering experiment with gold foil and see what we can learn about the nucleus. And then a follow-up tutorial, we'll talk about other experiments that were performed over the ensuing decades where we fired in different particles that had different properties that allow us to probe the nucleus in greater and greater detail. And so by the late 20th century, mid to late 20th century, we had a much more complete idea of what's going on at that very, very tiny region. So we're going to start with the gross properties of the nucleus and how we discovered them, much of what we already know, but get in more detail, and then move on to the finer structure. Okay, so I have a schematic here of a little bit more detail of the gold foil experiment. Okay, what's important about it is we have an alpha particle, all right? Again, an alpha particle is really just a helium nucleus, a mass of 4, atomic number of 2, so in other words 2 protons and 2 neutrons. And the key thing about that is not only does it fairly massive, it has a positive charge. Okay, Rutherford chose that for a very specific reason because he's trying to investigate the positive distribution of matter in the atom, and so he's going to rely on Coulomb repulsion as the main mechanism for deflection. So he has the gold foil where those nuclei are embedded, okay, and one of the key things we'll talk about later, so if this is gold, I'm sorry, not U, that's uranium, Au, aurum, if you were speaking Latin, okay, is that its atomic number is 79. Its mass isn't so important here. And that was known at the time. And so he just looks at this scattering angle. So if it goes straight through, that's a 0 scattering angle, and if it goes off at someone, he has some fluorescent tube and a microscope. We can see that. And he just plots the distribution. And we kind of already have a qualitative idea of what that distribution is. We've talked about it before. Okay, so off to the side here, we have that, right, most of the... and I'm not putting a number here, most of the scattering are 0 degrees. A few are a little bit more, right? Maybe between 0 and 90 degrees. And then it turned out, statistically, 1 in 8,000 had a scattering angle of greater than 90 degrees. In other words, it turned around. Not necessarily completely, but it came back in the same general direction. And Rutherford never expected that. Okay? So what we're going to look into this one more and more detail, because it's kind of a neat little derivation we can do, is we can use any alpha particle that comes more or less straight back and what we know about Coulomb repulsion to deduce something very specific about the nucleus. Okay, but before we get to that, let's look at some of the results. We already know about, but we can talk about a little bit more detail. The only way you can get a scattering angle greater than 90 degrees is for the target nucleus mass to be greater than the incoming alpha mass. And that can be understood fairly easily from conservation of momentum. So off to the left here, we have represents the gold nucleus, and here we have what we now know as a smaller particle. But how would we deduce that that nucleus has to have a much greater mass? Well, we're going to assume it's an elastic collision. Okay, so we're assuming the positives and the positives pushing on each other, and it's like a spring. As they get closer, you're compressing a spring, so they're not really come in contact. And we know that if the scattering angle is greater than 90 degrees, there's some component of the velocity of that alpha particle, right, that's what this is showing right here, is coming back towards us. And the only way that can happen is when we have an elastic collision. Remember, momentum is conserved and kinetic energy is conserved. And we work out the details. The only way you can get some of the motion to come back at you is if the incoming particle is less mass than the outgoing part or the target particle. So that was important. And so in this particular case, right, these are the deflections that are 90 or greater. So in some test questions, you want to understand what the angle is measured relative to. Next, if we look at all the angles, and this is what Geiger and Marsden did, right? They didn't get the Nobel Prize for it because they were grad students at Rutherford, and I want to give you just a little bit of a background here. So Rutherford won the Nobel Prize, I think it was in chemistry, not so much physics, because he came up with a formula that matched the data that Geiger and Marsden found. Okay, so the dots are the data, the solid line is the formula, and Rutherford worked it out. And we're going to do a very crude derivation of what he worked out, or not even necessarily that, because it's actually fairly complicated, but we're going to look at some aspect of it. And so what we notice from this, if this is scattering angle there, that the amount of the frequency which it occurs, which is the y-axis, drops off probably exponentially, not necessarily an inverse relationship. Okay, so that's what reflects what we've talked about already. Okay, and so let's talk about why he used alpha particles as probes. So based on the plum pudding model, Rutherford, that's what he was working on. That was the best we knew at the time. Expected the mass of alpha particles to go through the electrons undeflected. Again, he had no understanding of or expectations that there would be a lot of mass in the positive. Sorry, I don't know. I'm trying to talk at the right same time. I should say undeflected. Okay, so that was the expectation. The positives in the gold nucleus would just be smeared around such that there's no way, if they're scattered all over the place, there's no way they're going to be able to take a fairly massive, okay, even though helium is not a massive particle, it's much more massive than an electron, which was known at the time. Okay, and obviously the results contradicted expectations. And because of those results, he could deduce that the positive charge, i.e. the protons, interacted with a tiny but massive nucleus via Coulomb repulsion. Okay, so I alluded to that earlier. That's how they were able to deflect at especially significant angles. All right, and the kinetic energy of those alpha particles, in other words, coming out of that radioactive material in the box, could be used to deduce the extent of the nucleus. In other words, if you want to know how big is the nucleus compared to the atom, we could do some very clever derivation, which we're going to do right now. So let's go to the next page. So we're going to derive the nuclear size, okay, and then we're going to actually do it in a different way with a different set of experiments. So let me draw a picture somewhere. I'm going to draw pictures. So let's represent, right, the gold nucleus, our target, right, as a bunch of protons and neutrons. And again, he doesn't know that there's neutrons there at the time, but if he sees results, he's going to say, okay, it would seem that there's a lot of positives concentrated there. And the overall charge of that, we're going to call big Q, where big Q is essentially Z, right? The atomic number, the number of protons there. And that's just in units, we can multiply it by the Coulomb constant, but we'll worry about that later. And then we have our probe coming in, which is, we're going to call little q, that's our alpha particle, and we know that Z is 2 in this case, or its charge is 2. I don't know why that just got smeared out, but we know that. We'll fill that in later. So if this makes sense, is if this particle, which is also positive, in fact, why not even draw it as a circle? I'll just draw it as a little moving positive sign, right? The circle around it. If this is coming in with a certain kinetic energy, as it approaches the nucleus more or less head on, other angles it's going to deflect, but the very few that more or less come back, it's going to start feeling a repulsion, right? And that's a Coulomb repulsion. So what's going to happen is it's going to slow down. And if it has just the right energy, it's not going to hit the nucleus, but it's going to come to a stop and then be repelled away. And so we can use the concept of conservation of energy to figure out basically what the nuclear extent is based on how far away it is from the nucleus when it comes to a stop. And how far away it is, we're assuming, is right at the, if you will, the outer edge of the nucleus. Now remember, don't forget the nucleus is just as much a wave, so there is no real extent, and the Heisenberg uncertainty principle reinforces that. But at the time, we're going to pretend that the nucleus is definitely a hard, and now we know it's kind of more fuzzy, just like the electrons are. So in the derivation, in the rare instance where the scattering angle is 180 degrees, the kinetic energy, and that's important that we know what it is, of the alpha particle goes to 0. Okay, as I mentioned before, eventually it's going to come to a stop when it's fairly close to the nucleus. And for an instant, all of its energy, it just doesn't disappear. Where does it go to? Okay, think about that for a second. Pause. What type of energy does this alpha particle have when it comes to a stop there? All right, well, it's going to be a potential energy. Not a spring potential energy, because there's no literal spring there. It's not gravitational potential energy, because gravity is not the force that's affecting anything. It's electrical potential energy. This is a Coulomb forces that we're talking about, and we've already learned how to model electric potential energy. So, how do we model that? Well, let me call that a U, just to be consistent. Well, that's equal to the Coulomb's constant. And then, if you recall, you go back to your notes, or excuse me, your reference tables to find this. I'm going to remind you that the definition of electric potential, V, is energy per unit charge. So energy is QV. And when you have a point source, right, V is KQ over R, so this becomes K, big Q, that's the source of the charge, that's our nucleus, little q, that's our alpha particle, all over R. So that's how we learn to calculate it, and technically there should be a negative in there if it's attractive, or positive in this case because we're repelling. Long story short, this is K, Q, Q over R. And in terms of what we have in terms of nucleus, this we're going to call K, well, I've already done that, right? This Q is the Z of the gold nucleus, and this little q is the Z of the helium nucleus, okay? So it's just the charge of each one based on the number of protons. So in this case, Q is 2e, and this is 79e. And R is the nuclear extent. So we can now solve for nuclear size. So we can say, okay, the loss in kinetic energy of the alpha particle, so I'll put an alpha there, equals the gain in electrical energy, or electric potential energy of the alpha particle. So we can say, what is that energy? Well, remember, he was using 4.2 MeV alpha particles based on the decay process that occurred, I think, in the polonium or thorium. So if we convert that to joules, which we'll do here, we got 6.72 times 10 to the negative 13th joules. So we know that those alpha particles are coming in with that. So negative of that is the loss in that is, we're not going to worry about that. So that's just 6.72 times 10 to the negative 13th joules. Okay, that's going to equal, all right, now I'm going to use this equation right here, and I'm going to plug in the numbers I know. So K is 9 times 10 to the 9th, and I'm not going to put units. All right, our Q1 is 2. I'll convert it to coulombs in a second. The other Q is the gold nucleus, 79. And then what I would do is multiply it by 1.6 times 10 to the negative 19th. And I got to square this because I got to do it twice, one for each nucleus. And then I divide that all by R. Okay, so solve for R. I'll do the numbers for you, and you get 5.4 times 10 to the negative 14th meters. And so for the first time in history, we have an idea of how small the nucleus is. It's on the order of a femtometer, 10 to the negative 15th, whereas it was known at the time that the R of an atom is around 10 to the negative 10th, maybe 10 to the negative 9th for a gold atom. It's going to be a little bit bigger, but we see that there's a huge difference, and that's where we first learned that the atom is mostly empty space. All right, so I'm going to conclude here for this first one, and then we'll pick up with some follow-up equations, ideas, and other experiments that were done later in that century to give us even more detail about the nucleus, or an alternate way of finding the radius.